Hello and welcome back to my channel. Today we're going to be looking at the water cycle and water insecurity. It's the detailed revision over here on my channel. There's loads of these already up, so make sure that you've seen them, and without further ado I'm just going to get straight on into this. I imagine this to be about half an hour, 40 minutes of just going through the water cycle and water insecurity A-level revision, or the A-level unit, and this is like a detailed overview of the whole thing. So let's get straight into it. The global water budget. The water cycle is comprised of many stores, the largest of which is our oceans, which contain 97% of global water. Only 2.5% of our water storage are fresh water, of which is 69% glaciers, ice caps and ice sheets, and 30% is groundwater. Surface and other fresh water only accounts for about 1% of global stores. Other surface and fresh water is also made up of permafrost, lakes, swamps, marshes, rivers and living organisms. So let's talk about the hydrology in different regions. Hydrology in polar regions. 85% of solar radiation is reflected. Permafrost creates impermeable surfaces, so nothing can saturate those surfaces. Lakes and rivers freeze. There is rapid surface runoff in spring. The seasonal release of biogenic gases are released into the atmosphere as the permafrost thaws, as the top layer of the surface begins to thaw out, and orographic and frontal precipitation are most common in these areas. Comparing that to a tropical rainforest, the hydrology there is lots of dense vegetation which consumes 75% of the precipitation, meaning there is limited infiltration into the ground. Deforestation leads to less evapotranspiration and precipitation. There are very high temperatures, it's very humid, and the rainfall is convectional. The ITCZ, the Intertropical Continental Zone. The Earth consists of 6 cells of circulating air which form the globe's climate control. For the Northern Hemisphere, which is also true of the South, just in opposite directions. At the very top we have the polar cell, or the very bottom as well if you're talking about the Southern Hemisphere. This is where cold air sinks near the Arctic Circle, cooling and condensing to form precipitation over the northern latitudes. The air then travels southwards, heating it until the warm air meets the feral cell, which is the one below that. The air then rises, causing dry conditions for the land beneath, and then travels northwards, cooling as it does. Below that, as I've mentioned, we have the feral cell. This is the middle cell of the ITCZ and tends to be at a mid-latitude location. The air circulation in the feral cell is determined by the Hadley and polar cells on either side, similar to a cog system. And then at the very middle, so around the equator, the Hadley cell sits. Air rises and travels upwards from the equator, then sinks as it meets the colder air of the feral cell. At this meeting point, precipitation tends to occur. The air then travels southwards, heating up as it does. It will then have heated sufficiently to rise up at the equator again, commencing the cycle again. Drainage basins. A drainage basin is an open system operating within the closed system of the global hydrological cycle. It's defined as an area of land drained by a river and its tributaries, with a boundary known as the watershed, usually comprising of natural features such as hills, mountains, things like that. The basic flows, inputs and outputs are on this picture for you. On a local scale, the water cycle is also an open system. This is a process of water inputs, outputs and throughputs. But on a global scale, the water cycle is a closed system, a system that has no inputs and outputs, but only throughputs. The water cycle contains flows and transfers, inputs, outputs, stores and components. Inputs into the drainage basin. Precipitation. Precipitation is caused by the cooling and condensing of water and moisture in the atmosphere, forming clouds that release moisture in the form of rain, snow, hail, sleet, etc. Primary factors affecting volume or the condition of precipitation are as follows. One factor, seasonality. In some climates, such as monsoon or Mediterranean, there are strong seasonal patterns of rainfall. Therefore, the time of year determines the precipitation input within the drainage basin. Secondly, variability. Sudden or long-term changes to the climate can happen, which would affect precipitation levels, and so the drainage basin as a whole. There is secular variability. This is long-term, for example, as the result of climate change. There's periodic variability, such as annual, seasonal, or in a different monthly context. Stochastic variability. These are random factors like localization of a thunderstorm. Another factor is latitude. The location of the drainage basin has a major impact on climate, and so the volume and type of precipitation falling is also influenced as well. In most cases, the higher the latitude from the equator, the colder the climate. So, as snowfall occurs more often than rainfall. Also, at latitudes where air cells converge, the ITCZ, which we talked about briefly earlier, the climate will be characterised by the rise and fall of the air. Types of rainfall. Convectional rainfall is often a daily occurrence. The morning heat warms the ground, which turns heat into low-level moisture, or plant dew from surface stores. This moisture evaporates and rises. As the air rises, it cools, and moisture within it will condense to form rain, and turn as moisture accumulates to rainfall. In tropical climates, convectional rainfall is most common. Within tropical rainforests, rainfall occurs mid-morning before the temperature rises too high for condensation to occur. Another type of rainfall, frontal or cyclonic. This is where two air masses meet. The wedge can occur of hot air within the cold air. This is called a depression. At the front, where two air masses meet, warm, moist air is forced upwards above the cold air mass, causing the warm moisture to cool and condense to form cyclonic precipitation. Depressions are very common in the UK. Approximately 100 depressions hit the UK every year, and that might increase with climate change. And then relief or orographic rainfall, where warm, moist air, often travelling onto land from the sea, meets an area of high relief, such as hills or mountains. The air mass is forced to rise above the hill and to continue travelling. As it rises, the air mass cools, and then the moisture within it condenses to form clouds and rainfall. Orographic rainfall depends on the relief and the location of the land immediately after the sea. Many coastal landscapes are too cold, low-lying, or hills are set too far inland for relief rainfall to occur, but it is very common in Wales, which is what we see as the air masses move over Snowdonia into the east, further east. So the Midlands is typically a lot wetter due to this orographic relief rainfall over the Snowdonia mountain range. Fluxes and flows within the drainage basin. There are many flows within the drainage basin, many due to gravity, and so depending on the relief of the land. These flows occur at different speeds, which can influence many things like water balance and the likelihood of flooding. Interception. Interception is the direct intervention of plant leaves, changing the direction or temporarily stopping precipitation as it falls to the surface. Any moisture retained by the surface of the leaf, the interception store, is generally greatest at the start of storms, as plants' interception capacity varies on the type of vegetation. Infiltration. The movement of water from the surface into the soil. The infiltration capacity is the maximum rate at which water can be absorbed by the soil. It can be affected by soil composition, so sandy soils have a higher infiltration rate compared to clay. Past precipitation, the saturation of soils will reduce infiltration rates, hence surface runoff increases after a long, intense period of rainfall. The type and amount of precipitation. Dense root growth can inhibit the infiltration of water, and inception of plant leaves will delay infiltration. Compaction of soils will also reduce the infiltration rate and the relief of land. So sloped land will encourage more surface runoff, and therefore less infiltration as a direct result. Surface runoff. Water flows overland rather than permeating deep levels into the ground. Overland flow occurs where the gradient of land is greater, so when the land is flat it's more likely to infiltrate, whereas if it's on a hill it's more likely to just run down. Surface runoff is the primary transfer of water to river channels, hence heavily influencing their discharge. Through flow. Water moves through the soil into streams and rivers. The speed of flow is dependent on the type of soil. Clay soils have a high field capacity and smaller pore spaces, and so have a lower flow rate. Sandy soils drain quickly because they have a larger field capacity, larger pore spaces, and natural channels from animals such as worms. Some sport fields may also have sandy soils to reduce the chance of waterlogged pitches, but this may also increase the flood risk elsewhere. Percolation. Water moves from the ground or soil into porous rock or rock fractures, deeper bedrock and aquifers. The percolation rate depends on the fractures that may be present within the rock and the permeability of the rock. Groundwater. The gradual transfer of water through porous rock under the influence of gravity. Water can sometimes become trapped within these deep layers of bedrock, creating aquifers and long water stores for the drainage basin. Outputs of the drainage basin. There are three main outputs into a drainage basin. Since the basin is an open system, often water and moisture are transferred across the watershed. Evaporation. This is the loss of water moisture from the surface of a body of water, the soil, and the interception storage, on top of leaves, to the atmosphere. Evaporation rates increase when the weather is warmer, windier, and drier. Alternative factors also influence evaporation rates. Volume and surface area of the water body. The larger the surface area, the faster the rate of evaporation. Vegetation cover or built environment surrounding the water. Anything that reduces direct sunlight to the water body will reduce evaporation. And the colour of the surfaces beneath the water. Black tarmac, for example, will absorb heat faster than white snow, and so evaporation will occur faster on the tarmac. Transpiration. This is the biological process where water is lost to the atmosphere through pores of plants. Transpiration rates are affected seasonally, the type of vegetation, moisture content of the air, the time of day. So the morning dew is the release of moisture through transpiration in temperate climates. Stores. There is soil water, where water is stored in the soil and is utilised by plants. Groundwater. This is water that is stored in the pore spaces of rock. River channels, water that is stored in a river. Interception, water intercepted by plants on their branches and leaves before reaching the ground. And surface storage, water stored in puddles, ponds and lakes, etc. The water table is the upper level at which the pore spaces and fractures of the ground become saturated. It's used by researchers to assess drought conditions, health of wetland systems, and success of forest restoration projects. The factors influencing a drainage basin. Physical factors. You've got climate, which influences the amount of rainfall and the vegetation growth. Soil composition, which influences the rate of infiltration and through flow. Geology affects percolation and groundwater flow. Relief, so as I said earlier, steeper gradients of land will encourage faster rates of surface runoff. Vegetation, this affects interception and overland flow and the size. The larger the basin, the more precipitation generally. Anthropogenic or human factors. Cloud seeding, firstly, where substances are dispersed into the air to provide something for condensation to occur on. This was used in China right before the 2008 Beijing Games to try and reduce pollution levels. Secondly, deforestation. Less vegetation means less interception, less infiltration, more overland flow, leading to more flooding, and the cycle speeds itself up. Afforestation. More vegetation means interception, less overland flow, and more evapotranspiration. Dam construction. Dams reduce downstream river flow and discharge, increasing surface stores, and so there is more evaporation. Change in land use. Infiltration is 5 times faster under forests compared to grasslands. Converting land to farmlands means less interception, increased soil compaction and more surface runoff. Groundwater abstraction. When water is taken out faster than the water is recharged, groundwater flow decreases and the water table drops. Irrigation. A drop in water tables due to high water usage. And urbanisation. Impermeable surfaces reduce infiltration, increase surface runoff, river discharge increases, and the cycle speeds up. Water balance and river regimes. The water budget. In the short term, water availability varies between different days and months. Over long periods of time, surpluses and deficits can cancel each other out. Precipitation is equal to the discharge, the evaporation, plus or minus the change in stores. Look at this diagram. Precipitation is greater than evaporation. Therefore, the soil's moisture increases, creating a soil moisture surplus. Point B. As temperature increases, the rate of evaporation will increase. The soil uses the moisture gained during its surplus through soil moisture utilisation. Point C, the top of that curve, the point of maximum evaporation. This is the point of highest risk of drought. Point D. Despite evaporation decreasing, there isn't enough precipitation to provide for vegetation use of water loss. Therefore, there is a soil moisture deficit. Points E and F. As precipitation rates exceed evaporation rates, soil will regain moisture and reduce its deficit through soil moisture recharge. River regimes. A regime is the annual variation of discharge of a river at a particular location. Most of the river flow isn't from immediate precipitation, but is supplied from groundwater between periods of rain, which slowly feeds water into the river system. There can be seasonal variations of the regime, periods of high discharge followed by periods of low discharge, which are due to glacial meltwater, snow melt and monsoons, which can cause sudden fluctuations in river input. Complex regimes tend to occur for larger rivers, that is, across different relief and climatic zones, such as the Ganges River and the Mississippi. The factors affecting the characteristic of a river's regime include the channel capacity of the river, the area and relief of the drainage basin, the volume, pattern and intensity of precipitation, the climate, the geology of the soil, the anthropogenic or human activities such as building dams or terracing the land. Storm hydrographs. Storm hydrographs represent the variation in discharge within a short period of time. These are days rather than years. Before a storm begins, the main supply of water to the river is through groundwater or base flow. However, as a storm develops, infiltration and surface runoff will increase, which causes a greater through flow. The features of a storm hydrograph. The rising limb. The increase of river discharge, not necessarily instantaneous after precipitation. The peak flow. This is where the maximum discharge occurred after the maximum precipitation has occurred. The lag time is the difference between the peak precipitation and the peak discharge. The falling limb of that graph is as the storm precipitation levels decrease, discharge in turn will decrease over time. And then the base flow. Eventually the discharge returns to its normal level. Factors influencing hydrographs. Physical factors. A flashy storm hydrograph will have a short lag time, high peak and steep rising limb. This is typical in intense storms, which exceeds the infiltration capacity of soil, or when rapid snowmelt happens as temperatures suddenly rise above 0 degrees, or low evaporation rates due to low temperatures. The rock type might be impermeable, like granite, which encourages surface runoff. There may be low infiltration rates in the soils. There are high and steep slopes, so more surface runoff of the relief of the land. It's usually a smaller basin when we see a flashy response. There's often also low vegetation, less interception, and more rapid movement of water. And the basin might already be wet from previous rainfall. But a subdued or a slower storm hydrograph response has a long lag time, a low peak and a gently, slowly rising limb. This is where we might see steady rainfall, less than the infiltration capacity of the soil, slow snowmelt as temperatures rise very slowly, high evaporation rates due to high temperatures, more permeable rocks like limestone which allow for infiltration and reduce runoff, high infiltration rates into the soil as well. A larger basin, this is more typical of too, more highly dense vegetation, so there is more interception and more evapotranspiration. And then if there's not an exceeding a pre-existing condition like a dry basin and a low water table. The soil is also often unsaturated, so there's more chance of infiltration. And a human activity that might influence this is afforestation, rebuilding those forests to allow for more interception. The management of drainage basins. Attempting to manage drainage basins sustainably can be challenging. Some river management schemes tend to try and reduce runoff from precipitation, therefore reducing the risk of flash flooding or storm flow discharge by growing vegetation on roofs to increase interception and temporarily store some water within plants. They can create permeable pavements, such as gaps within paving blocks to increase infiltration and reduce surface runoff on the roads. Rainwater harvesting, collecting rainwater to use as domestic grey water, or creating wetlands. These are areas with marsh and wetland vegetation that will act as natural sponges and increase temporary water storage. Alternatively, trying to manage the anthropogenic impacts on a drainage basin can also be challenging. Allowing human development on a basin can outweigh the need for sustainable management due to population or housing pressures. Impacts can include deforestation, tree felling and slash and burn. Soil becomes exposed and roots are lost, which binds the soil together, which leads to more soil erosion and so more surface runoff. Or impermeable surfaces. As more tarmac and concrete is laid, less infiltration into the topsoil can occur, and so more surface runoff occurs. Bridges can act as dams for rivers, restricting river flow, especially storm flow, and increasing the pressure of a river's water, increasing the pressure a river is under, therefore worsening the flood impacts. And drainage and sewage systems will reduce lag time, and so a quick flow of water back to rivers, increasing the risk of flash flooding. Deficits in the hydrological cycle. An imbalance of inputs and outputs can have serious implications for the hydrological cycle. A deficit, more commonly known as a drought, refers to when input is less than output. This deficit can be caused by natural and or human factors. The meteorological drought. The rainfall deficit sees low precipitation, high temperatures, strong winds, increased solar radiation and reduced snow cover, which leads to a loss of moisture, irrigation supplies drop, and there is a reduction in water available for consumption. Hydrological drought, stream flow deficit, sees reduced infiltration, low soil moisture, little percolation of groundwater and recharge, which results in reduced storage in lakes and reservoirs, less water for urban supply, poorer water quality and threats to wetlands and habitats. Soil moisture deficit, agricultural drought, sees low evapotranspiration, reduced biomass and a fall in groundwater in the groundwater level, which results in poor yields from rain-fed crops, falling irrigation systems or failing irrigation systems. Livestock productivity fails, rural industries are affected, and government aid may also be required. And then a food deficit, so socio-economic drought. This sees a loss of vegetation, increased risk of wildfires, soil erosion and desertification, which leads to widespread failure of agricultural systems, food shortages, the rural economy collapses, rural to urban migration is required. Often we also require international aid, and sometimes in this sense there's also a humanitarian crisis. El Nino Southern Oscillation. El Nino is the change in water patterns within the southern hemisphere, leading to unusual weather patterns. The causes of El Nino aren't fully understood. Normally cool water is found along the Peruvian coast, and warm waters are found around Australia. ENSO causes this to switch. Peru gets warmer, whereas Australia gets cold water, and usually occurs between every 3 to 7 years, generally lasting for about 18 months. Peruvians can determine ENSOs based on their anchovy harvest. Anchovies prefer cool waters, therefore as the water warms up due to El Nino, the anchovies migrate away, causing a reduction in Peruvian harvest. ENSO can also trigger extremely dry conditions in areas of South and Southeast Asia, Eastern Australia, Northeast Brazil. In South Asia, ENSO can weaken the annual monsoon. Functioning ecosystems. Wetlands. Wetlands act as a temporary water source within the hydrological cycle, which can help mitigate from river floods due to sudden storm discharge. Chemically, wetlands act as giant water filters by trapping and recycling nutrients and pollutants, which helps to maintain water quality of the river. Wetlands have a very high biological productivity and support a very diverse food web, providing nursery areas for fish and refuges for migrating birds. All these functions contribute towards their natural importance, as well as a value for human society. For example, providing fish for food or a clean water supply. The value of wetlands. Supports life, stores and flows carbon through vegetation and soil or peat. There's nutrient recycling. There's a provision of resources, so fuel wood, fisheries, mammals and birds for tourism. It regulates conditions, so the regular supply of groundwater and so the water-based flow of a river. It provides water purification and there is a reduced flood risk. And then the cultural value. There's aesthetic value, there's recreational use and there's cultural heritage. Meteorological droughts have a major impact on wetlands. Reduced interception due to less precipitation will cause vegetation to wilt and die, which in turn impacts soil nutrient levels and the rest of the complex food web. Desertification, the physical causes. Reduced precipitation. As vegetation dies, the protective layer it provided for the soil will also be removed. As a result, the soil will be increasingly exposed to wind and rain, which may accelerate the top rate of erosion, leading to worse soil conditions. This may cause a positive feedback loop of worsening soil, vegetation death, desertification. Global warming. The rise in average climatic temperatures will increase the rate of evaporation of water moisture, especially in tropical and sub-Saharan climates. If more moisture has evaporated, less will be available for convectional rainfall, and so plant growth will be stunted, and if vegetation dies, leading to desertification. Human causes. Population growth is the root cause of the recent increases of desertification. As populations increase, demand for food, water and other resources also increases. As pressure for food increases, agricultural methods change to supply the demand. For example, cattle farming is becoming intensified, resulting in large areas of forest being cut down to provide enough land for grazing. Intensification of crop farming, meaning that the fallow time between crop harvest and new planting will be reduced. These farming practices can cause overcultivation, trampling of vegetation and loss of soil nutrients, which reduces soil fertility. In addition, forests may be felled or slashed and burned to make room for new farms or housing, further worsening soil quality and exposing the topsoil to erosion. Over time, desertification will escalate into a positive feedback loop. Surpluses in the hydrological cycle. All drainage basins are vulnerable to surpluses in water. However, some locations are more susceptible to flooding, such as low-lying land, the base of a river and estuaries. River flooding can occur along with groundwater flooding as the ground becomes saturated. Therefore, any surface close to the water table is vulnerable to flooding. Urbanised built environments. Impermeable surfaces increase surface runoff, reducing lag time and so increasing the risk of flash flooding. Small basins, especially in semi-arid environments and arid environments. These regions suffer from flash flooding due to short lag times, which can be hazardous. Mitigation and adaptation to flood risk. Afforestation of upland areas, increasing vegetation cover will reduce rapid surface runoff. Restricting construction of floodplains, which reduces potential economic and social losses for residents living on a floodplain. Also, by reducing urbanisation, there will be maximised levels of interception. Establishing temporary extra floodplains. In the event of extreme weather, some UK councils have designed football pitches or parks next to the river to channel some of the storm discharge and reduce the risk of flooding for towns living close to the flood banks. Impacts of climate change on the hydrological cycle. Anthropogenic global warming is due to increased greenhouse gases in the atmosphere. This could lead to several different impacts, directly affecting the hydrological cycle. If land and sea surface temperatures continue to rise, the periods between ensocycles, which is currently every 2 to 3 years, could decrease. This would lead to more periodic, unusual climates for both South America and Australia. Increasing global temperatures would increase rates of evaporation, which could lead to potential droughts and increasing water scarcity. However, for some locations, the rise in average temperature will lead to more convectional rainfall and enhanced tropical cyclone or depression intensity. This in turn will cause more intense and periodic flooding. Climate change will reduce inputs, reduce stores, and may increase outputs with the hydrological cycle. There'll be less precipitation, less water available in stores, reduce the size of snow and glacier mass. Water tables will drop in height and the capacity of the groundwater store and aquifers will deplete. High rates of evaporation and more frequent cyclones and monsoons. However, it's important to note that since the future of drainage basins within the hydrological cycle depends on climate change and ensocycles, both of which are unpredictable and not very understood, managing future change is challenging, if not impossible. Inequality and insecurity over water. Water is spatially distributed unevenly across the globe. 66% of the world's population live in areas that only have access to 25% of the world's annual rainfall. Conflict can further limit accessibility to water sources. Demand has risen because of population growth. Generally, more people, so more water is needed. A growing middle-class population, as countries develop and industrialise, therefore increasing lifestyle and domestic demand. And economic growth, which means industrial demand may also increase. However, supply cannot meet demand since aquifers and deep water wells are being dug, especially for water-intensive agriculture. Water tables, groundwater storage, are dropping as a result, and water is being extracted at a faster rate than the soil is able to recharge. Causes of water insecurity. Precipitation varies across climates. Mid-latitude areas generally receive the most rainfall. Topography is also significant because areas of high relief tend to get more precipitation, and surface runoff is also greater, with more inclined planes. So channel flow tends to be larger and so water can be easily stored in dams and reservoirs. And geology also determines water security or water insecurity. Permeable rocks can be infiltrated and water can be easily stored underground. However, humans are also reducing supply through pollution. Industrial activity, especially in developing countries with slack environmental laws and population pressure, lack of treatment of sewage and the plastic tide, are reducing accessibility to clean fresh water. In addition, saltwater encroachment due to over-extraction and rising sea levels, climate change, is further reducing freshwater stores, hence increasing water insecurity. Consequences of water insecurity. As a result of the limited supply, the price of clean water has increased in certain regions and may increase globally in the future. Water is very important in economic activity, crop yield and manufacturing capacity. Agriculture consumes about 67% of all water extractions, and industrial water consumption is on the rise, especially in developing and industrialising communities. Fields and grazing lands are dependent on rainwater, and aquaculture for fish farming has been on the rise, as wild fish supplies have diminished. Over 20% of all extracted water is used in industries for energy production. Solutions to water insecurity. Many solutions are dependent on reducing water consumption, such as many farmers focus on storing rainwater to use for irrigation and greywater purposes. There has been an increase in HEP and the generation of energy without the consumption of fresh water. Other solutions include hard engineering schemes such as megadams, which can provide a large volume of water, generate HEP and reduces the demand for groundwater. But it floods land, it's expensive, and countries or areas downstream often suffer from a lack of water. As water is stored on the surface, it gets evaporated quickly. Desalination plants provide a large volume of clean water and reduce the demand on groundwater, but it's very energy intensive, releases lots of CO2, it's expensive, produces salt waste, and it's expensive to build and maintain. And then water transfer schemes. These can provide water for areas that lack water and in arid areas. Water can become a resource that is very valuable for people in poor and undeveloped countries. But these can dry up source areas. They're expensive, there's lots of evaporated water, and people need to be relocated to construct these. The Water Poverty Index. The WPI is an index used to measure localised water stress for the use of national governments to improve provisions. The WPI focuses on 5 components: water resources, the availability of water; access to water, the distance from safe drinking, cooking, cleaning, industry, water; handling capacity, so management, infrastructure and income; the use of water, so domestic, agricultural or industrial purposes; and environmental indicators, such as the ability to sustain nature and ecosystems. The WPI is scored similarly to the Human Development Index. Each component is scored out of 20, giving a score between 0 and 100. 100 meaning no stress, 0 meaning water stress and deficits constantly. The highest scoring country on the WPI is Finland with a score of 78, while Haiti has the lowest score of 35. Sustainable water management. Sprinklers are automated spray technology, or advanced irrigation systems are more efficient. Recycling city water is a relatively cheap method of conserving fresh water, especially in areas of extremely high demand. Grey water doesn't need to be cleaned as much to meet drinking standards, and therefore is less energy intensive. GM crops are being developed. Many are tolerant of dry and saline conditions. Domestic conservation includes installing smart meters, charging more for water during times of day where there's a lack of water supply, using eco kettles, taking a shower instead of a bath. The restoration of lakes, rivers and wetlands, increased natural water storage, and restoring meanders and replanting vegetation. Integrated water resource management. The IWRM approach emphasises the river basin and the logic geographic unit for strategic planning. The basin is treated holistically to protect the environment and ensure fair distribution. This should have freedom from corruption, environmental protection, food and water security for poorer people, effective dialogue between people, a decentralised approach, cash recovery of schemes through effective pricing, and effective regulation and planning use. Groundwater management. This is where we see aquifer storage and reuse, and groundwater quality and quantity modelling. Waterway management sees river rehabilitation, sustainable water allocation and environmental flows. Integrated urban water management sees water treatment technology, water sensitive urban design and water harvesting and reuse. And then monitoring technology uses sensor technologies and real-time wireless monitoring and controlling. Water sharing treaties. Under the Helsinki rules, international treaties must contain concepts like equitable use and shares. The criteria could be based on natural factors such as rainfall amounts, discharge and the size of the drainage basin. Social and economic needs, so pollution size, welfare of people, development plans. Downstream impacts, reducing flow, restructuring flow, water tables, pollution. Dependency, the ability of alternative sources. Prior use, the tricky question of existing historic rights and future potential use. And efficiency, avoiding waste and mismanagement. Different organisations are involved in promoting effective water management schemes. The UN ECE Water Convention promotes joint management and conservation of shared freshwater ecosystems in Europe and neighbouring areas. The UN Watercourses Convention offers guidelines on the protection and use of transwater boundaries. However, the WWF agrees that most agreements lack appropriate enforcement and monitoring. Key players in water management include the UN, so the UN ECE, the UN Economic Commission for Europe Water Convention, aims to protect and ensure the quality of sustainable use of transboundary water resources. The EU Water Framework Directive, agreed in Berlin in 2000, targets to restore rivers, lakes, canals, coastal waters to suitable condition. And then national governments. So, for example, the UK's Environment Agency, which checks the compliance with EU frameworks. And that is the end of this water cycle and water insecurity detailed revision over here on my channel. I hope it's been useful. There's been a lot of words coming out of my mouth, but I hope this is useful just as a fairly quick 40-minute summary of everything that needs to be covered in this unit. So let me know which one you'd like to see next. I have 3 more that I need to film and get up for you, but yeah, let me know, and I will see you in my next video. Subscribe down below and I will see you soon. Bye guys.